How does superplasticity prevent materials from breaking? Have you ever wondered how some materials can stretch and bend without breaking? This ability is linked to a fascinating property known as superplasticity. Today, we will look at how superplasticity helps materials withstand stress and avoid breaking. Superplasticity allows materials to undergo extremely large plastic deformations, often over 1000% elongation, without necking or fracturing. This remarkable ductility happens under specific conditions. These include high temperatures, usually above half the material's melting point, and a very fine grain size, typically less than 10 micrometers. When these conditions are met, the primary mechanism at work is grain boundary sliding. In simpler terms, the tiny grains in the material can slide past each other smoothly. This movement accommodates strain without concentrating stress in one area, which is what usually leads to cracks or breaks. To understand this better, let's start with the basics. Ductility is a material's ability to deform plastically without breaking. Most materials fail when they experience localized thinning or necking. This concentration of stress leads to cracks. Superplasticity enhances ductility by changing how deformation occurs at the microscopic level. Instead of dislocations moving through grains, which can cause strain hardening and eventual failure, grain boundary sliding allows grains to move relative to each other. This movement helps distribute strain more evenly across the material. There are several key factors that enable superplasticity. First, a fine grain structure is essential. Small, equiaxed grains increase the total grain boundary area. This increase facilitates grain boundary sliding. The fine grain size is often stabilized during deformation by the presence of a second phase that prevents grain growth. Second, high temperature plays a significant role. Elevated temperatures increase atomic mobility and grain boundary diffusion. This makes sliding easier and allows the material to deform extensively without damage. Lastly, a low strain rate is important. Slow deformation rates give grains the time they need to slide and accommodate strain without creating stress concentrations. When materials meet these conditions, they can deform like a viscous fluid instead of a brittle solid. This behavior prevents the initiation and propagation of cracks that lead to failure. This characteristic is especially important in applications that requiring complex shaping or forming of metals without compromising structural integrity. Industries such as aerospace, automotive, and medical device manufacturing benefit greatly from superplasticity. It provides a way to avoid catastrophic failure modes by enhancing ductility for beyond normal limits. Instead of breaking under stress, superplastic materials can absorb and redistribute strain, delaying or preventing fracture. Understanding superplasticity helps engineers design components that resist failure. By exploiting superplastic behavior, they can work with metals that are prone to brittle fracture under conventional conditions. This knowledge is essential for creating reliable and durable products in various fields.